Welcome student to the Web Optics course. So in the last class we discussed about the coherence length and what is the meaning of coherence, etc. Now in today's class, which is lecture number 14, we continue with the concept of coherence. So the calculation that we started in the last class, that we are going to continue. Okay, so we have today lecture number 14, and the concept was we have a source here and then with two different paths. This is S and we had S1 and S2. So light are reaching some arbitrary point P. Light is first goes here via S1 and S2. The light is reaching here at some point P, suppose. So want to find out what is the intensity at point P, and in order to calculate that, so what we find, let me write down that the intensity at the point P is intensity due to the wave that is coming on from S1, source S1, intensity for the source S2 and their interference term, half of epsilon naught C, and then we had 2 of real part of then E1 and E2 star. That was the interference term. Then I know what is my E1 and E2. E1 is related to the source field like this, T minus T1, and E2 was related to beta 1 E T minus T2. They are related to the source E1, E2 is related to the source S, the source field S with this form. Then we introduce this into here in E1 and E2, this with the form E, and also we have the explicit form of E as E equal to Et is equal to E0 e to the power of minus I omega t e to the power of I phi t that we had. Now imposing these, we get, let me write here, IP is equal to I1p plus I2p plus epsilon naught C, then beta 1, beta 2, real part of E t minus T1 and E t minus T2, average of that. Star, we are going to get a star here. Okay, then we try to find out what is this term. So E t minus T1 and E star T minus T2. That quantity one can have as E naught square e to the power of minus of I omega T minus T1 e to the power of I omega T minus T2 e to the power of I phi T minus T1 and e to the power of minus I phi T minus T2. This is the way we can write this quantity E T minus T1 star E star T minus T2. Now, if I write T minus T1 rescale to some T, then T minus T2 I can write as this is equal to T minus T1 minus T2 minus T1. I just rescale that T minus T1 is T. If I rescale T minus T1 is T, T minus T2 in terms of T minus T1 I write this. So this is essentially T plus tau, delta T plus tau or delta T. Let me write it as tau, where T minus T plus tau, where tau is equal to T1 minus T2. So let me erase this completely. So this is T plus tau. Okay, so with this new notation, I can have new rescaling factor. I can have IP, the irradiance at point P is equal to I1P plus I2P plus epsilon naught C beta 1 beta 2, the scale factor due to amplitude reduction, and then real part of ET new rescaling, and then E star T plus tau. This is a very important factor in understanding coherence. This is called the correlation function. This is called the correlation function, that is correlate the electric field at point at some time t to multiply it by the complex conjugate of the same electric field at some later time t plus tau, and this is given by a factor gamma. So gamma tau is a function of tau is the average time average of this quantity, this physical quantity Et and E star T plus tau. So that factor is called the correlation factor or correlation function, and I can normalize this with this. I can normalize this function this correlation function as gamma. So gamma tau, I can define gamma as half of C epsilon naught beta 1 beta 2 whole divided by root over of I 1p I 2p. So once I write gamma, small gamma in terms of big gamma, then this IP, whatever the IP I wrote, is become a very compact form, and this is I1p plus I2p plus 2 of root over of I1p I1p root over of I2p multiplied by real part of gamma, which is a function of tau. Okay, so essentially this is the term that is the heart of the interference. So this term is the heart of the interference term, and it is a function of tau. Therefore it is a location of p as well, because tau is the time difference between tau was t1 minus t2, that is the time difference between the time of flight of two waves reaching at point P. So tau is a function of gamma is a function of tau, and it depends on the location of P as well. So this gamma, essentially this gamma tau is the term essentially called degree of coherence. This is called degree of coherence. Now let us find out how one can find this degree of coherence, and let me see, because I know the explicit form. So gamma, big gamma tau, that is equal to E naught square, and then the time average of these terms. So if I write down the time average, it is e to the power of minus of I omega t into e to the power of I omega t plus tau, and then the phase term e to the power of I phi t multiplied by e to the power of minus I phi t plus tau. I just simply write down the expression that we had. Now e to the power I omega t and e to the power I omega t here cancel out. So only thing that we have e to the power I omega tau, which is not dependent, which is the time difference between the time of flight. So I can take it outside. It should not be a part of the time average. So it should be E0 square e to the power of I omega tau. In the bracket we have e to the power of I phi t into e to the power of minus I phi t plus tau, t plus tau, time average of all these things. Now when we have the time average, we know that if I have a function time average of the function if t, then by definition it is 1 divided by t 0 to t, that function dt. This is the way we make a time average. So here also our goal is to find out what is the time average of these things. So e to the power of I phi t to the power of minus I phi t plus tau time average is 1 divided by time, a large time over which I want to integrate this term. So it is e to the power of I phi t minus phi t plus tau bracket close, I integrate over time, so dt. Now this quantity is basically gives us how the phase of the two corresponding wave will change over this time tau. So that one can realize with this figure. So for we already had this figure that once we have the radiation, these harmonic waves are emitting, but it is emitting without phase relationship with a very long period of time. After some point it breaks and we have radiation like this, where no phase relationship is there. So let me draw it once again. So there is a sudden phase jump here. So on. So since there is a phase jump from this point, if I draw this phase jump, in the same plot, then it looks like it goes here and there is a jump here, and then it goes here, there is a sudden jump here at this point, like a step function. Then it goes here, there is a sudden jump here, then it goes here, there is a sudden jump, and it goes here, there is a sudden jump. And this drawing is suggests that this is for phi t. Over the time, this is the way the phase changes. Now the same thing one can have for another time, and that is for phi t plus tau. And when we have t plus tau, we will get a similar curve, but there is a jump here, and then there is a jump here, then there is a jump here, then there is a jump here, and there is a jump here. So we will have this jump but at different time, and this different time is essentially, this time is essentially tau. So from here to here we have tau, from here to here we have tau. So over this I plot time, and this is happening for a time period tau 0, that is the coherence time. So at this point it is tau 0, at this point it is 2 tau 0, At this point it is 3 tau 0. At this point it is 4 tau 0, and so on, because it is happening at the period of say tau 0. Now when we find out the difference, because if you carefully note that it is phi t minus phi t plus tau, that was t plus tau, that was the term we need to calculate. And if I plot that again, in a same plot, so I am plotting here phi t minus phi t plus tau, then we get a step function like this. Maybe it is in positive side, negative side, there is a random, so it can have certain jumps, and we are going to get some blocks like this. So from here to here it is tau 0 minus tau, and this is tau naught, and this, for this function, this height say h1, and so on. Over the time I have this picture. Okay, so once we have these functions, let me call this function as delta phi function of t. So I can write down that delta of phi is equal to 0 when t is in between t tau 0 minus t and 0, that is in this region, but it has a value h1 when the time t takes the time this to this. So this is the way the function delta phi is changing. It takes some value when the t is in the interval of t naught, tau naught to tau naught minus tau. So now let me calculate the time average of these things. So gamma, small gamma tau, that was the degree of coherence, which is essentially related to big gamma tau, is proportional to that quantity 1 by t, this integral, time average 0 to big T e to the power of I delta phi t dt, that is the quantity. Now note that for large t, we can have many periods, so that is equivalent to n multiplied by tau naught. Tau naught is the period. So the integral that we have, gamma tau, with certain constants, it will be e to the power of I omega tau, that was already there, multiplied by the integral of this, so 1 divided by n tau naught, and then integral 2 part 0 to tau naught minus tau, where the function phi is 0, so we will have e to the power I multiplied by 0 dt, and other part which is tau naught minus tau to tau naught, and we have e to the power of I h1 dt. Okay. Now this term is also there for next, so we will going to get a, this is for n equal to 1, but a similar term because we have h1, h2, h3 etc. So like this, here we have another, so this is h2, this is h3 and so on. So I need to integrate over all the discontinuities where the during the place where there is a phase jump. So if I start adding all these terms, so similar, so we will going to get similar terms for n minus 1 successive intervals. Similar successive terms we are having. So what value then gamma we are getting from here? Gamma tau is e to the power of I omega tau divided by n tau naught, and then I am getting this integral, and when we have, I get tau 0 minus tau plus this value. So it is, if I do the integral, it will be I tau and tau minus this thing. So essentially I get plus tau e to the power of I h1. That is my first term. Similarly, my second term will be tau naught minus tau and then plus tau e to the power of I h2 and so on. A large number, n is a large number, so I have something like this. So my gamma, that is the degree of coherence that I wanted to find out, will be related to a term like e to the power of I omega tau divided by n of tau naught, and if I accumulate all these terms, tau minus tau 0 minus tau 0 minus tau, tau 0 minus tau, all these tau 0 minus tau, I accumulate, there will be n number of tau 0 minus tau, so it should be n multiplied by tau naught minus tau, that will be one term, and then there will be a sum over tau. If I common, there will be a sum over j equal to 1 to n e to the power of I h j. Okay. Now hj is a random nature, as I show. Because of the random nature, this sum, whatever the sum, that should vanish. So I should write, because of the random nature of hj, the summation sum should vanish for large n. The sum should vanish for large n, sufficiently large n, this quantity should vanish. If it does, then what value essentially we get? So is, if that is the case, then from here we can write gamma tau is essentially equal to e to the power of I omega tau divided by n of tau naught multiplied by n into tau naught minus tau. So n will going to cancel out, and essentially we have something like 1 minus tau divided by tau naught into e to the power of I omega tau. Now if you go back and check, then we need to essentially find out the real value of gamma tau. That was the term that was sitting there in the interference, the intensity calculation. The interference term is related to real value of that. So when we put the real value, then this becomes 1 minus tau divided by tau naught into cos of omega tau. So this is basically the magnitude of the degree of coherence. This is the magnitude of the degree of coherence. So if I just consider that what is the mod value, because this is the magnitude, and from this equation gamma tau, if I only take the magnitude, so it is essentially the gamma tau is essentially the term 1 minus tau naught, whereas gamma tau is, you can write mod of gamma e to the power of I omega tau. Real part of this gamma tau is mod of gamma and then cos of omega t. So because of this term, actually what we get is, sometimes we get this is basically the interference term, and I can get, so let me go back and check what was our I. So our I was the interference term related to this. So let me write down IP was I1P plus I2P plus 2 root over of I1P root over of I2P, and then the important term, real part of this. So real part of gamma tau. That was the expression we start with. That is the main expression, and this is the interference term. And now we are in a position to find out, we know that what is this this quantity, real part of gamma tau. Based on that, this value can give 0. Based on this value, it can give 1 or it can give minus 1. So when so I can define also something called visibility. Visibility is when this is, let me write down first, this is I max minus I min divided by I max plus I min. That is the visibility. Now let us concentrate on this term and try to find out what is happening. So let me go one by one, that and then we are going to finish after that. So 1. So we write as complete incoherence. So what is the meaning of complete incoherence? When this tau tends to tau naught. That means the value of mod of gamma is tends to 0. If that is the case, then we simply have the interference of two wave is intensity due to that is intensity due to the single summation of the intensity of these two single sources. I can write it as 2 of I naught if these two sources are equal for equal source. Equal source. For equal source, this is 2p. And what is the visibility? If I find out the visibility, it should be 2 I naught minus 2 I naught divided by 4 I naught. So there will be 0. So visibility will be 0. So when we have complete incoherence, then there will be no visibility at all, because these two waves are simply cancelling out. As cancelling out means there will be no correlation between these two. However, when we have complete coherence, then tau is 0. Tau tends to 0. That is the condition for complete coherence. If that is the case, the mod of gamma, that is the degree of coherence, is 1, and the real value of gamma tau is simply mod of gamma cos of omega tau. So IP in that case becomes I1p plus I2p plus 2 root over of I1p I2p and cos of omega tau. Now this cos of omega tau has a maximum and minimum, so I can write I max as IP. This is basically I1p root over of I1p plus root over of I2p whole square of that. That is the I1, and if I1 and I2 they are same, then this value is 4 I10 for same source. Well, for I minus, in that case, IP minimum will be root over of I1p minus root over of I2p and whole square of that. So that is essentially 0 for same source. So I can have the visibility in this case 4 I naught divided by 4 I naught, which is 1. Very strong visibility one can have, and this is the most ideal case when we have two coherent source interfering. But that is not the case always. The general case that we always get is the partial coherence. That is the topic that we start with. So partial coherence is the case we always have, where tau is in between 0 and the coherence length. So that means mod of gamma, which is degree of coherence, is in between 0 to 1. Then IP will have something like I1P plus I2P plus 2 root over of I1P, I2P, then real value of gamma, and I don't know what is the value of the gamma definitely, so this value will remain. For same source, it is 2 I naught and then 1 plus root over of sorry, it's not 1 plus root over of, this is just gamma, 1 plus real part of gamma for equal beam, And if somebody wants to calculate that what is the V visibility, I will not going to do this calculation, rather I ask the student to please check it using the formula I max minus I min whole divided by I max plus I min, and that value essentially gives you mod of gamma, so degree of coherency. So that is the visibility one can find out. So today we don't have much time to explain more about the coherence, the different aspects of coherence. So I'm going to stop here. Hopefully you understand I did all the detailed mathematics with the physical correspondence to make you understand that how when two light are coming from a same source but to different path, there is a time lag, and this time lag how leads to the concept of degree of coherence, and we get the partial coherence, the concept of partial coherence. And when we have a absolute coherence, then the visibility, the way we defined, is maximum. That means if two waves are interfering, we are going to get a very nice interference pattern. In the later part of this course, we are going to see that. However, if there is no coherence, I mean the coherence, two beams are not coherent to each other, we are not going to get any visibility is 0, so we are not going to get any kind of pattern formation. So that's why interfering two light will be visible in terms of the production of the pattern, different kind of fringes will be understood, will be depends on the coherency, the something called a property, something called coherence. That means how the source is emitting continuous harmonic waves and how the source is monochromatic. If it is highly monochromatic, it is expected that it will generate a very lengthy harmonic wave, and we will going to get sufficient coherence length, and we will going to get a very strong fringe. So in the next class we will discuss another aspect of this coherence in terms of wavefront, which is called the spatial coherence. In order to get a nice beam a fringe pattern, also the spatial coherence is important. So we are going to understand what is the definition of spatial coherence and how this spatial coherence is important in generating different fringes. So with that note, I like to conclude here. Thank you very much for your attention, and see you in the next class for more. Thank you.